All right, welcome. I'm delighted to see so many people here tonight for what is going to be a wonderful, engaging presentation. Before we move to that, let me just make a couple of quick announcements. We have an amazing lineup coming up this fall. If you're not on the MOMATH mailing list, it's not too late to join because our next events blast telling you about all the exciting things is going out toward the end of this week. In case you want to know just a little bit of what's coming up this Friday, if you like puzzles, we will be puzzling with pentominoes with Vince Matsko, a mathematician coming to us from the Bay Area in California. This Saturday, if you haven't checked out our wonderful Math of Origami exhibit upstairs in our gallery, you have an exciting chance to tour it this Saturday with the curator of the exhibit. So if you haven't seen it, it's a really wonderful exhibit. We expect it to show up in the New York Times sometime next month. And so you can see it here and see it first and see it with the curator. Next week, we also have another edition of our visiting scholar Peter Winkler's session on puzzles. And so if you love puzzles, come learn from one of the foremost puzzle experts in the world. That's next Tuesday. Followed by Wednesday, Math Encounters. We're going to talk about paradoxes and probability and why we're all so bad at figuring out what the odds are. And following that, later that weekend and the following week, we have the people who created Sudoku coming to MOMATH. And I'll just mention one more as a sneak preview because I'm super excited about this one. John Edmark, who's the creator of the Bloom exhibits you see back there and who you may have seen on Science Fridays, is returning for one night only on October 13th, and we expect that to fill quickly because he's an absolutely phenomenal presenter. So mark your calendar for that. Get on our mailing list so you don't miss any of our upcoming exciting activities. But with that, I'm delighted to tell you all that the National Museum of Mathematics has been partnering with Dr. Moira Dillon at NYU for over a year now. We've been doing lots of studies and research about how children learn mathematics and how they perceive different geometric figures. And Moira has been a wonderful, wonderful partner for us. And it's thanks to her and her Lab for the Developing Mind that we're able to bring you this exciting speaker tonight. So I will turn it over to Dr. Moira Dillon to give you a bit more of an introduction for tonight's speaker. Thank you.
Thanks, Cindy, and thanks to the National Museum of Mathematics for collaborating with my lab for a while now. As Cindy mentioned, we've been able to be here to do some exciting studies together. Maybe some of you in the audience have participated in those studies. And basically what we're aiming to do is try to understand how kids come to understand those formal conceptions that are at the foundations of the kinds of school learning of mathematics that we're all interested in figuring more and learning more about. We're collaborating on a number of new programs here at the museum, and we're here tonight for one of them, the Minds on Math Talk series. So over the next 5 years, Minds on Math, which is co-sponsored by my lab, the Lab for the Developing Mind at NYU, and the museum, and supported by the National Science Foundation, will feature accomplished scholars in developmental psychology, cognitive science, mathematics, and education who conduct research on how our minds and brains learn and appreciate math and related fields. The lab and the museum will also offer complimentary family events, free with admission to the museum, where content of the talks will be transformed into engaging activities for parents and children alike. So our first family event will take place on Sunday, October 6th from 10 a.m. to 1 p.m., so come visit us then. So this evening, we're really thrilled to welcome Dr. Elizabeth Spelke, the inaugural speaker of this exciting series of talks. She is currently the Marshall L. Berkman Professor of Psychology at Harvard University. Dr. Spelke is also the director of the Laboratory for Developmental Studies at Harvard. Dr. Spelke has received many prestigious accolades for her work, too numerous to even list here, but I note in particular the Jean-Nicot Prize for Interdisciplinary Research in Cognitive Science and the C.L. D. Carvalho Heineken Prize for Cognitive Sciences. Dr. Spelke has also been a fellow of the American Academy of Arts and Sciences since 1997. Dr. Spelke's work has revolutionized the field of developmental psychology and cognitive science, and this is an understatement. Her studies using ingeniously crafted behavioral experiments with young infants and children have identified the cognitive sources of our uniquely human achievement of mathematics. Dr. Spelke's work also extends beyond the study of our developing representations of quantities, shapes, and spaces. She's also charted the foundations of human knowledge about objects, actions, and people. Dr. Spelke exemplifies the interdisciplinary cognitive science, the interdisciplinarity of cognitive science, working across disciplines from philosophy to computational modeling. In collaboration with economists, she's also begun to take her research from the laboratory into the real world, using randomized controlled experiments to evaluate educational interventions, ultimately to enhance young children's learning. It's this last component of her research program, bringing cognitive science into the field, that she'll discuss with us today. And so it's with particular pleasure that I introduce Dr. Spelke as the inaugural speaker of Minds on Math. Dr. Spelke was my doctoral advisor, and I have seen firsthand, as a result, her incredible ability to synthesize basic laboratory research into comprehensive theories of cognitive development. What's more, she's able to translate such research beyond the lab to help shape the lives of children of all backgrounds in the noisy and complex environments in which knowledge actually grows. To me, she exemplifies the term professor because she's able to profess not just her knowledge, but also her passion for the human mind, indeed for every human mind. Please join me in welcoming Dr. Elizabeth Spelke.
Thank you, Molly. I'm sorry, I know I should say Dr. Dillon, but I can't quite get myself head wrapped around that. That was a completely over-the-top introduction I have to get you back and say, from a completely over-the-top former graduate student whose energy just ignited my lab and took it in a million directions that it never possibly would have gone in without you. And I'm delighted to see that you're now joining forces with this wonderful museum, not only to advance your own research program, but things like this talk series and the activities that you're having in 2 weeks and everything. I think that's just amazing. Now, you said that I'm an interdisciplinary developmental cognitive scientist. I'm actually not. I'm a humble developmental psychologist who does behavioral studies of primarily these creatures over here. And I like to think that we can learn something about human minds in general from studying infants and seeing what they do and how and what they don't do and how their knowledge grows. But I also think that behavioral studies in themselves are really limited. So one talent that I'm willing to admit that I have is a talent for becoming friends with people who are in other disciplines and then coming to collaborate with them so that we can try to triangulate in on basic fundamental properties of human minds that allow us to develop knowledge in such an immensely broad array of different domains. Knowledge that centers in each domain on highly abstract principles, and there's no domain where this is clearer than the domain of mathematics. So the hope is that through interdisciplinary work in developmental cognitive science, including work in psychology like the stuff I'll talk about today, but also work in anthropology and linguistics and other fields that goes out and looks at people living in extremely different circumstances, in different cultural traditions, and asks what's universal and what's variable about the development of human knowledge. Research in neuroscience, people who go into the brain and try to figure out what underlying mechanisms are producing the things that we see when we do simple behavioral experiments. And finally, people in computer science, especially artificial intelligence and machine learning and computational modeling, that attempt to understand the functions that the human brain and mind are engaged in at a mathematical level, what the fundamental operations are that give rise to knowledge. So the points I want to make tonight, focusing primarily on the findings of behavioral experiments on infants and young children, but seconded, I think, by research in all of these other fields, is that when we look at the early development of our understanding of fundamental concepts at the foundations of mathematics, like concepts of number and concepts of geometry, we see some really striking sensitivity as early as we can look to abstract mathematical properties of the world. But we also see that tasks that seem simple to us now can be extremely difficult for young children. So there are ways in which math is easy for them, and there are ways in which math is hard. And I want to start by just giving you some examples of some of the ways in which math is easy. So I'm starting with an experiment by Véronique Guizard, which was conducted on newborn infants in a French maternity hospital, a couple days old on average. She studied them in the hospital, bringing them into a little room that she had set up for doing experiments, and started them off by playing for them a sequence of different sounds. Now, the sounds she used were speech syllables, only because kids are really attentive to speech and interested in it. And she presented each syllable repeated in repeating sequences. And for half the babies, each sequence had 4 long syllables in it. For the other half the babies, each sequence had 12 short syllables in it. So the durations of the sequences and the numbers of sequences were the same, but within each sequence, the number of syllables differed. And after babies listened to that for a minute or so, she showed them simultaneously an array of objects. And on alternating trials, there were either 4 objects or, oh, we have a baby here, that's great. Either 4 objects or 12 objects. And she simply looked at how long the infant looked at the visual display while continuing to listen to the sound. And the question was, would babies be like we are in a fitness center or someplace? If there's TVs, multiple TVs around, but one of them we can hear the sound to, we're more likely to look at that. Will they be more attentive to a visual display that corresponds to the sound? And what she found in this first experiment was that they were. The babies looked about twice as long at the array of objects that corresponded in number to the sound. She obtained that in a couple of experiments and only got this effect to decline in a final experiment where she made the numbers closer together. So instead of 4 versus 12, it was 4 versus 8. So this experiment and others that followed in a series after this first one provided evidence that even newborn infants are able to match numerical arrays both across modalities, audition and vision in this case, but also across different formats, a temporal sequence of sounds versus a simultaneously present spatial array of objects. And they seem to do this with approximate precision. They're not matching numbers exactly. Nevertheless, it's pretty safe to say that these infants on day 2 of their lives, they have heard speech in the womb, but they haven't had a chance to experience numerical conjunctions of this sort. Yet they're demonstrating sensitivity to them, suggesting that already at the beginning of life, we're sensitive to certain aspects of number. Here's another way in which math is easy. This comes from an experiment conducted longer ago by Karen Wynn. She worked with 5-month-old infants and presented them with a puppet show, which I will lay out for you here just as a sequence of images. There's a puppet stage, and a hand places on the stage a toy mouse. Then a screen rotates upward so the mouse is covered, and a second toy mouse is placed on the, behind the screen, next to where the first one had been standing. Now the question to the baby is, what's back there? And to get the baby's answer, infants subsequently were presented with 2 different displays. On half the trials, the screen was lowered to reveal 2 mice. On the other half of the trials, it was lowered to reveal either 1 mouse in this first study, or in a follow-up study, 3 mice. And the question was, how long would babies look at these displays? Now here the assumption was different. The assumption was that when babies see things that happen in a predictable sequence, they'll be interested in that sequence and will continue to look at it. But if something unpredictable happens, that will especially boost their attention to that scene. They'll be searching for why this unpredictable event occurred. And indeed, what they found in this case was that when the screen was lowered to reveal the wrong number of puppets, the infants looked longer than they did when it revealed the correct number, providing evidence that the babies were able to represent the successive hiding of each of these two objects and keep track of how many objects were participating in that event. Here's another case with somewhat older babies showing an extension of this ability. In this study, infants were initially presented. Now they're old enough that they can crawl, so aren't restricted to looking at looking time. And infants viewed two empty boxes initially, and then they saw a person put one at a time 2 cookies into one of the 2 boxes. And then one at a time 3 cookies into the other box. And then the person simply lowered their head and mom said, okay, you can go, kid, now. Which box of cookies do you want to go to? And the kids crawled reliably to the box that had 3 cookies over the box that had 2. So putting these 2 studies together, it seems like in addition to having a sense of approximate numerical magnitude, which the first study with the newborns showed, it looks like quite young infants, as young as 5 months at least, have a sense of exact number when they're presented with objects one at a time, and they have to accumulate information over time. It looks like they're capable of tracking up to 3 objects in parallel, and they can do this for by 10 months at least, for 2 separate arrays, holding all of that information in mind simultaneously and make a comparison, answering the question, which of these boxes has more? So they seem to be able to represent small numbers of objects exactly, and in some sense as ordered magnitudes. Okay, a couple more examples. I think this may be my last infant example, but this was an experiment by the great Dr. Dillon with 7-month-old infants conducted in my lab and involved presenting babies with sequences of images. So the way the study went is that simultaneously 2 triangles were presented to the left and right of a large screen that the infant could look at. They stayed present for less than a second, and then they were replaced with 2 more triangles. Now, displays kept changing over time, and each image would present the triangles at a different orientation and at slightly different positions. But there was one key difference between the 2 streams. In one of the 2 streams, here it would be the one that's on the left, the same shape triangle is appearing at different orientations and slightly different sizes and positions in each image within the screen. On the other side, there's 2 triangles of different shape that are appearing in alternation. And the question was, are infants going to be sensitive to this difference in shape on the right and to the sameness of shape on the left over all of these changes in the orientations of the triangles and the exact position within the image in which they're appearing and so forth? And she found that they were. The infants looked reliably longer at the stream with the changing shape than at the stream with the constant shape, suggesting basic sensitivity to geometry. Here's another study from much earlier, from the person who was Dr. Dillon's advisor before I was, Barbara Landau at Johns Hopkins. She ran this study both with a single blind child, but also with a whole group of sighted children who participated in the study blindfolded. And the question was, can children use basic geometrical properties of their movements through space to guide their navigation in a situation where they have no visual information to go on, nothing's been explained to them in advance? Will they spontaneously recruit a sense of the geometry of the environment in their navigation? So to ask this, she put this blindfold on the child while the child was seated in a chair, then helped the child get up from the chair and led the child from the chair to a toy truck in a different part of the room. Oh, I should say, yes, no, I didn't animate this right. The toy truck and the basket were not there until after the child's blindfold went on. So initially, the child only saw the chair and an empty room in front of her. But then, after she was blindfolded, the truck and the basket were put out there, and the experimenter led the child blindfolded to the truck and said, let's pick up that truck and go put it in a basket. And she led the child over to the basket. And then she said, okay, can you bring the truck and the basket back to your chair? Okay. So the child had been led on the first two legs of the triangle, but the question was, could the child use the, side angle side theorem to determine the distance and direction that she needed to move to get back to the chair, sorry. And indeed, children did this. As in everything I'll tell you about infants, with approximate accuracy, not exact accuracy, but took off in approximately the correct distance. And in variations of the study where the chair was actually taken out of the way, moved to approximately the right, they went in the right direction to approximately the right distance to get back to the chair. So young children seem to be tracking, in the studies on the left, properties of shapes of objects or shapes of forms, like their relative distances and directions, because they're perceiving invariances here over changes in orientation and some changes in size. Whereas here, they seem to be showing sensitivity to the absolute distances and directions that they move as they're moving through a layout. And in other studies that we and others have done, infants similarly show sensitivity to distances and directions, not when they're blindfolded, but when they're sighted, in an environment where they can use things like perturbations on the floor or the walls of a room to track where hidden objects are. They will relocate those objects by drawing on memories for the distances and directions at which they had seen things as they were navigating. So infants and young children also seem to be sensitive to not only to aspects of number, but to aspects of geometry. Okay, a couple more examples of math being easy, but we're gradually going to be moving up to older kids. These are studies of preschool children. And they asked children not simply to detect geometry in an immediate display like a room or a display of objects, or to detect number in a visual image or a sound sequence, but rather to use spatial symbols. So these children were 4 years old. Of course, they're very familiar with pictures as symbols, pictures as representations of the world. And so they were presented with a special kind of a picture. It presented nothing but it captured nothing but the geometric structure of a larger environment that the child was in. So the child was in a room in the real studies. Here we did some versions of them outdoors as well, where 3 cans were arranged in a triangle, and the picture simply had 3 dots in a similar arrangement, of course presented at a much smaller scale and at a different orientation relative to the orientation of the room, of the cans on the floor. And the child was simply, the experimenter simply pointed to one of the 3 dots on the picture and said, can you put the ball in the can that's at that location? And the child had to then go to the actual array, figure out which of the 3 corners of that triangle was the corresponding one in order to solve this task. And interestingly, children were able to do this with no instruction. They weren't told, this is a map, here's how you're supposed to do this, you should need to line it up, nothing like that. It was simply spontaneous, and this is another case that was really easy for kids, given that they understood how symbols work by 4 years of age, how pictures work. Picking up on the geometry that connected a picture to an environment was easy for them. Here's another task that was partly easy for primary school children. These are children who were simply shown arrays with small dots and line segments, and they were told this small dot is a picture of a point. A point is so small it has no size at all. And this little line segment is a picture of part of a line. The line is so thin that the real line's too thin for you to be able to see it, and it keeps going on after the ends that you see here. Okay. Now, let me ask you some questions, and here's an example of one, right? Basically, you're able to ask children questions about all of Euclid's axioms and postulates pertaining to points and lines in arrays like this. And children as young as about 7 were able to answer these questions consistently and in accord with the principles of Euclidean geometry. So it looks from this like children are spontaneously able to use spatial symbols by the time they've had some experience with pictures and other kinds of drawings, other kinds of spatial symbols. They're able to use them to reason both about depicted environments in the case of the maps and about abstract objects in the cases of the points and lines with no specific instruction. It seems as if this is another case where reasoning about geometry comes naturally to kids. Okay, let me get back to number for a minute. We're moving up to older kids. This is from a study that was conducted in India with children who sell in markets. These were mostly about 10 to 13-year-old children, so not super young children, but they were their families were merchants, and they would help out during the hours when they weren't in school selling in markets. And to see how good they were, a bunch of economists posed as customers, extremely difficult customers who asked for unusual quantities of items that were being sold. They asked for 2 different quantities of 2 different kinds of items. And then they gave an amount that was an unusual amount. So they didn't just give a 1,000 rupee note. Maybe they gave a 750 rupees or something like that and asked for change back. And then when the poor child gave them change, they disputed it. They said, wait a minute, I don't think you gave me the right amount, so as to elicit from the child their explanation of, so the child could come, inviting the child to come back at them and say, no, look, this times this is this, and so forth. Okay, so children were extremely good at these market transactions, okay? They didn't do any written calculations. Occasionally, a child would make a little interim note of what the total cost of the first quantity was before going on, the first item was before going on to the second one. But in general, they solved these tasks without using paper and pencil at all, simply by mental calculations with high accuracy. And when they were pushed, their justification used, appropriately used, addition and multiplication to explain why, this many of this one plus this many of that one would yield this amount, which when I add what I gave you back to that, we get to the amount that you gave me. Now, this is not an isolated study. There have been much work by and cross-cultural cultural psychologists showing that all over the world, people with no formal education use mathematics in all sorts of different professions, from carpentry to farming, where you have to judge, given how far away one tree needs to be from all the trees around it, how many trees can I plant in this particular space, and so forth. And in every case, it's learned on the job. It's learned intuitively, not by explicit instruction from other people. Okay, final example from the Munduruku. This is work, an Amazonian group that's been studied a lot by Pierre Pica and Stanislas Dahan in comparison to educated people studied in France or the United States. And they were given tasks similar to the tasks that were given to children in the US, where they had to pick out similarities and differences among different visual forms or move to locations in space, and performed very, very similarly to educated adults in North America and Europe, and also were shown to share educated adults' intuitions about points and lines in the cases where our intuitions are clear. All of those seem to be ways in which math comes naturally to us, and math is easy. But each of these also has another side that suggests that points to areas of mathematics that are hard for children, and also hard for us as adults, relatively hard for us as adults. So I've already told you that these brilliant newborn infants represent number, but they only represent number imprecisely. And in fact, the ratio differences need to be large. So when the difference was reduced to 2 to 1, it looks like some of the kids were getting it, but performance is by no means as robust as it is with the 3 to 1 difference. In the Wynn experiments, the ones with the 1 versus 2 versus 3 puppets, Infants succeed when they're given arrays containing 1, 2, or 3 objects, but they fail when they're given arrays with larger number of objects, even when the ratios are large, if the objects are introduced one at a time. So in both of these types of experiments, children only see one cookie at a time, or they only see one puppet at a time. And under those conditions, they can distinguish 1 from 2 from 3, but they can't distinguish 5 from 10 or 3 from 6. They're strictly at chance when 3 cookies go in one side and 6 go in the other. So even imprecisely, in this context, they seem utterly unable to keep track of larger numbers. And further research suggests why. Tracking objects on the one hand, and assessing the approximate numerical magnitudes of sets on the other are highly distinct operations. And when they can be applied to the same array, when 6 cookies go in this side and 3 cookies go in that side, so you could either try to keep track of the individual objects or you could try to keep track of the set. When there's a competition between 2 tasks like that, children end up opting for one or they opt for the other. And whichever one they haven't opted for, they colossally fail at. So in this case, kids opt for tracking the individual cookies. And if there's 3 on one side and 6 on the other, they will have no guess as to which side is more numerous. So that's the first way in which math seems to be hard for kids. Here's another way in which math seems to be hard for kids. It comes up when you look at the most obvious thing that every parent sees their children going through sometime, starting around age 2.5, and really getting into high gear when kids are 3, when they start using number words. So children begin learning language actually before birth. Studies done on those newborn infants in Paris maternity hospitals, before they showed that babies were sensitive to number of syllables, they showed that they could detect the sound of their own language relative to the sound of non-native languages. So clearly they were already learning something about language before birth. And by the time infants are 6 months of age, they've learned enough about language that if you present them with images like a picture of a foot next to something else, and you say, look, foot, they will tend to turn and look at that object. So they're in general very talented at relating the words that they hear to things in the world. Now with that background, you might think that kids would be very quick to pick up on the meanings of number words, the ways in which number words relate to things in the world. And superficially, it looks like kids are good at this, because somewhere in the 3rd year, from about 2 years of age and up, children learn to recite the number words, and they learn the routine that looks by which people count. So this girl here was presented with 6 objects, and she pointed successively to each one and said 1, 2, 3, 4, 5, 6. The question is, though, what do these words mean? And to try to get at that, Karen Wynn, the same person who studied the 1 + 1 is 2 with the mice, with the infants, and who was certain that kids would get this right, gave kids a simple task. After having them count these guys to 6, she pushed them together into a pile and said, what are they? I think they're frogs. Can you give me 3 frogs? So what happens at this point is that the child would stop and look at the experimenter like, what is it you want me to do now? I just did 1, 2, 3, 4, 5, 6. Just give me 3, that's all, give me 3. So the child picks up 2 and puts them in the pond. And then the experimenter says, is that 3? And the child looks at her and picks up another one and puts it in, and then picks up another one and puts it in, okay? No idea what these number words mean. Actually, that's not quite true. They know that you're supposed to pick up a plurality of objects. They don't just pick up one when asked for 2 or 3 or 4. But otherwise, they're just random between those different numbers for quite a while after figuring out what the routine is supposed to look like of counting. So number words seem to be hard to learn, and that raises the question, what makes them hard? Is there some conceptual limit, or is it a language limit? Is there something about the way numbers behave in language that's different from the way words like foot behave in language that make numbers harder to learn? Or are they harder to learn because there's something about the concept of number that's causing kids problems? And to try to get at this question, two different investigators, pretty much in parallel, developed had the idea of testing for children's conceptual grasp of number without using number words at all, to see whether they were able to work out the logic of how number behaved in the absence of number words. So I'll tell you just about the task that Julian Hara-Ettinger did with a very interesting group of people, children living in the Bolivian Amazon, in a tribe called the Chimani, who attend school. And the Chimani language does not have number words in it. So everybody in the Chimani population uses Spanish for the Spanish words for numbers. But children start school at different ages, and some of them start school very late, others start school earlier, depending on how far away their village is from the nearest school, among other things. So there's a lot of variability in when school is starting. And so he took these children across a fairly wide age range and with a fairly wide range of experience with schooling, and gave them the following simple task. He lays out 8 cookies and says, these are your cookies. There's no number words. There's language in this task, but no number words. So he lays out 8 cookies, says, those are yours. Then he lays out 8 cookies in the same spatial array and says, these are mine. Do we have the same number of cookies, or do you have more, or do I have more? At that point, children will say they're the same. And then he takes them and scoops them into a pile, so it's no longer clearly, perceptually obvious how many cookies are there. At that point, kids again say, we have the same number. And now he performed one of a number of different transformations on one of the 2 arrays. One of the transformations was simply to scramble the cookies in one of the 2 piles and ask, do we still have the same number? Children would say yes with high confidence. Another thing was to remove half the cookies from one of the piles. Now children would say no with high confidence. We don't have the same number, right? That's an approximate numerical difference. So kids did very well at that task. On the other hand, when they simply removed 1 cookie from one of the piles, or they didn't remove anything, but they added 1 cookie to one of the piles, or they removed 1 cookie and then added a different cookie, not the one they had taken out, to the pile, now children were completely unsure. Not all of the children, but an important subset of the children got those problems wrong. And interestingly, it wasn't just because all of these changes took place, because there's another version of the task that they got right. If a single cookie was removed and then that cookie was put back in, now children knew that the numbers were the same. But if one was taken out and a different one was put back in, many of the children didn't. What this suggests is that young children don't spontaneously think about a collection like 8 cookies as, at one and the same time, a set with an exact numerical magnitude, and a set composed of individuals who are substitutable. The numerical magnitude could remain the same as the individuals changed. Now, interestingly, in the Chimani population, the kids who got all of these problems right were the kids who had been in school the longest and who knew the most Spanish number words. So language predicted this conceptual advance. But it doesn't seem as if the child's problem was simply a language problem, because these tasks didn't involve any numerical language at all. Okay, this is, I think, my final example of, no, second to last example of math being hard for children. Now, children throughout the developing world, children tend to be in school at all, even the poorest children living in countries like India, where much of the work I'll be talking about from now on took place. They're in school, and they're progressing through the different grades of school. But if you test them on their basic knowledge of arithmetic, you find that many of these poor children have failed to learn the basic material that's being taught in the early years of elementary school. So the best data on this comes from this wonderful organization, Pratham, that goes around the country and basically does a report card on every village in the country, asking simple questions of subtraction or long division or questions about geometry. They also do reading and other topics, simply to ask anonymously. They're not collecting data on individual children, but to see what proportion of the children who are in 4th grade in this community have actually mastered the 2nd grade curriculum, the 4th grade curriculum, and so forth. And the data are pretty sobering, that more than half of the children in India fail to master curricula that are several grade levels below their own current level. Now, because we were interested in these children who sell in markets, we wanted to see what the levels of performance of children who don't sell in markets would be if we go to the schools where the market children are attending school when they're not in the markets. So they're kids from the same neighborhood but with no market experience. And those children, the children that we looked at were on average in grade 7. They were about 13. And when we gave them these tests, we found that a fairly large number of them failed to master the grade 4 division problems. Most of them, but by no means all, succeeded at subtraction, but only a little more than half succeeded at division. But the most sobering thing was these tests are not timed, and children were allowed to write down the calculations that they did. And we looked at those calculations, and they were kind of sobering. So here's a child who was given a problem where they needed to buy 8 oranges at 20 rupees each. And you see what the child has done. He or she has written the word 20 8 times. Then they couldn't add all those 2's, so they added 2 plus 2 to get 4, and they wrote that 4 4s. But now they couldn't add 4 plus 4 plus 4 plus 4. So they turned to a rote memorized sequence of multiples of 4 and wrote down 4, 8, 12, 16, way higher than they needed to, up to 40. That's, I think, how it was learned in the classroom. And now they could go 1, 2, 3, 4 and write whatever this was, the 1, 6. It's not obvious they were even thinking about this as a numerical problem. This was the workaround they had so that when teachers asked them questions, they could give an answer. Now, these weren't the worst of the calculations. This was the worst, where a number like 23 is turned into tally marks, which are then counted in order to get to an answer. Now, we thought that the market sellers would be far better at all of these tests. Of course, the market sellers were extremely good at the market problems with the 8 oranges for 20 rupees each. But the market sellers were no better than the other kids in school at the school problems, the subtraction and division problems that are given on Pratham's test. They performed no better. And in fact, they looked at those problems and they said, oh yeah, I don't know how to do that. I can't do those problems. They're sitting in the classrooms. They've been in these classrooms for 7 years through the, starting in grade 1, exposed to math instruction. They know how to do math on their own, and they're not able to make that link. Finally, I guess I did have one more example. Finally, this wonderful work that Molly has done on a test that was used a long time ago and showed that adults, both in the Amazon and also in Boston, would give approximately correct estimates of the third angle of a triangle if they were shown the other 2 angles of the triangle. So Molly first wanted to look at this in more detail, and first did so by looking at younger children ranging in age from 6 to 12 years. And her questions were the following. Suppose you take these 2 angles of the triangle and you just make each of these 2 angles bigger. What's going to happen to the position of the third angle, and what's going to happen to the size of the third angle if you make these guys bigger? That's one question. Another question, suppose you just move them further apart. What's going to happen to the position and to the size of the third angle? And initially, the kids look like they're pretty good, because they say that if you move them apart, the position of the third corner is that it's going to go higher, it's going to go higher if you move them further apart, and it's going to go higher if you make those 2 angles bigger. But then the next question is, what's going to happen to the size of that angle? And here they got the answers exactly wrong. They said that if these two angles get bigger, the size of the third angle will get bigger. And furthermore, if you move these two apart, instead of the third angle staying the same, it'll get bigger. Okay? So they're systematically getting those answers wrong. And as they get older, they get closer to the right answer. But interestingly, now, first of all, a question was, do they just not understand the question that's being asked? Maybe they think that when you're asking about the corner, you're really asking about the whole triangle. Is the whole triangle getting bigger? So we tried variations on the language, got kids to understand that some corners are pointier than others, and they could find pointier corners. It didn't help. It wasn't a language problem. It was a conceptual problem. Now, interestingly, evidence from within the study itself suggested that children solve these problems not by invoking some abstract rules of geometry, but rather by doing a process of mental simulation. They try to imagine going upward toward that third corner. And the simulation isn't perfect, and errors get introduced. I think one of the most interesting things about this work came from follow-up work that Molly did with another collaborator at Harvard that showed that educated adults do the same thing. That if you're given these problems with triangles, we don't remember back to things like the three interior angles summed to a constant. Rather, we think about this particular figure in front of us, and we simulate an answer, and we make errors in the same direction that the children do. So this is a way in which I think geometry is hard for us throughout life. Okay, I'm finally done with examples. So we can get to questions. Why does math learning start so easily and then become so hard later? And more importantly, despite the fact that it's hard, math education is, at the end of the day, successful for most of us. What makes it successful? How do children develop the concepts and the skills of school mathematics? And finally, in light of this huge problem in the developing world and also in disadvantaged children in developed countries, underperforming in school, way below what we have every reason to believe is their inherent capacity, how can their school math learning be enhanced? Can we take any lessons from studies of the basic processes by which kids overcome the difficulties that the hard parts of mathematics present? And can we use that to enhance learning by young children? So here's the idea that's behind all of the work that my lab has been engaged in on this topic. We start with the idea that when you face any problem, including the hardest problems, you face them by drawing on what you already understand. And what we as a species already understand from the beginning, based on the things that we find are easy for infants and young children, are two aspects of number. That sets have numerical magnitudes, and that sets are composed of individuals who can be tracked over time, tracked in parallel, and compared to each other. And also two systems of geometry, one for capturing the shapes of small-scale forms, and the other for navigating through large-scale layouts. Now, these four systems are all early emerging. They all center on abstract concepts. They all remain present throughout our lives and are universal across cultures. And they're all limited. And a key limit is the one that I already mentioned, that different systems, when they need to be applied together to a single problem, spontaneously will tend to compete for attention, so that children, we can easily rely on one or another, but not easily combine them. But despite all that, research shows that each of these systems is linked to our abilities to go beyond them and learn school mathematics and formal mathematics. Sorry. So there's a number of different sources of evidence showing that approximate number representations relate to math learning. First of all, children's earliest number words tend to have approximate meanings. Before they learn to perform exact arithmetic, they can perform approximate arithmetic intuitively with imprecisely, but intuitively. This is, I think, probably where the market sellers begin. Children's core abilities correlate with their symbolic abilities. So if you take a large group of children and you ask, how sensitive to approximate numerical differences are there, you find that some children are sensitive to finer differences than others are, and that dimension of difference is predictive of children's learning of symbolic mathematics in school. And finally, studies show that if you take children who are in the process of learning symbolic mathematics and you simply give them exercises to perform with arrays of dots. So they see pairs of arrays of dots, say red dots and blue dots, and they have to judge which is more numerous, and the problems get harder and harder, they get closer together. That exercise shows benefits in the laboratory on children's subsequent performance of symbolic arithmetic. So these all say that there's connections between the early developing abilities and later school math. Further research in developmental cognitive science shows, though, that language and symbols also are predictive of children's success with hard math problems, and also adults' performance of problems that don't come naturally to us. So one of them that's known by anybody who speaks multiple languages is that when we have to do mental arithmetic in our heads, add up a bill at a restaurant and divide it up, we're going to do it in the language that we learned mathematics in. We don't just do it in a pure abstract language of thought. We use a specific natural language for doing that. We also know that children who, for one reason or another, have diminished access to the language of number will tend to have associated delayed number concepts. We know that impairments to language can bring calculation deficits. If you have a stroke as an adult, that impairs your language faculty. It often, not always, but often there will be impairments to your calculation abilities as well. And there are similar relationships linking core geometric abilities to performance of learning of Euclidean geometry and performance of in geometry classes. And of course, we all know that the symbols that we use for representing number can make an enormous difference in how easy it is to calculate with those numbers. All of these phenomena say that language and symbols are helping adults to think about math. And they raise the question, will they support children's learning of school mathematics? Well, here's a way in which they might. I said that there's this competition between seeing a group like this as a set versus as a collection of distinct individuals who are being considered in parallel. And when kids first learn to count, it may actually make the problem worse, because what they're being taught to do is to go 1, 2, 3, pointing to individuals, at no point drawing attention to the set as a whole in the way that counting is supposed to be used. However, when number words appear in ordinary conversations, simple properties of noun phrases seem to naturally and simultaneously call attention to the fact that there's a set here, you have a plural on the verb, but the set is picking out its members as individual cats, okay? So an expression like some cats can help you to see this as a set of individuals. And then further expressions like 3 cats can give you the idea that maybe these are words that are telling you something about the relation between the individuals and the numerical magnitude of the set. And then, of course, there are other sentences that you can get that are really informative about the meanings of number words, where within a sentence itself, you pick out individuals and summarize them with a numerical expression. So ordinary language expressions could be very helpful to kids in overcoming some of the limits on some of the things that make number concepts hard. I'm going to skip spatial symbols because I'm taking too long here. There's similar work, reason to believe that those could be helpful to kids, and that this helpfulness doesn't end at the end of the preschool years. As kids go on to learn the algorithms of arithmetic in primary school, symbols can be extremely helpful for showing how numbers can be decomposed by base 10, the basis for those arithmetic algorithms. Let me otherwise skip this, though, so that I can get to our studies in India. So the background for these studies is that a lot of work that suggested, primarily conducted in laboratories, not actually conducted in schools, suggested relationships between how kids would go on to perform at learning mathematics in school and the kinds of preschool activities that they had at home. That children who are in homes with mathematically literate adults who are able to play board games where you're counting out moves and comparing scores and so forth, getting a chance to, by playing, exercising both the language and the symbols of mathematics, come into classrooms more prepared with the kinds of skills that you'll need in order to face the hard problems of learning math in school. So that led to the development of a hypothesis about how one might be able to get kids to conquer the hard problems, the areas where math is hard. The hypothesis, I'll just show it pictorially, is that we start with a set of core abilities. Then over the preschool years, we come to master the language and the basic symbols of mathematics so that we can communicate about mathematics with each other. And then when we get to school, we're able to use language and symbols to represent more economically and conceive more clearly of how the notions of number and geometry that were easy for us can be fit together into a formal system that you can use to go beyond those initial notions. Now, this is a hypothesis about how kids learn in school, which means it's a hypothesis about how kids learn under very different situations from the situations in which people like me study them in laboratories. So homes and schools are social environments. When I do an experiment on an infant in the laboratory, I tell the infant's parent, do not talk to your child. Close your eyes. We want to know what this child is able to do on her own. Do not interact, okay? But if we want to understand how kids are learning in school, everything you learn, you are learning from other people. And you're learning it in this social context. It's a very different context. So hypotheses developed in the laboratory of what's going to work for children's learning, if we want to test them, we have to get out of the laboratory and into the environments in which children are actually going to be learning. So schools are social environments, that's a good thing. They're also noisy environments, that's potentially a bad thing. When we do hypersensitive experiments in the lab and see what abilities kids have under optimal conditions, that won't tell us in itself when they're going to be able to harness those abilities in the real world. So the way I think we need to advance on this problem of understanding how formal systems develop in our minds is we need to bridge what's best about the research in laboratories and what's best about field research and do both. Laboratories can be a good source of hypotheses about what could be going on in children's minds when they're in school. But we actually need research in the schools in order to see whether those hypotheses are right. So let me quickly tell you about 3 experiments that we did in India. We being the wonderful economist Esther Duflo, founder and co-director of the Jameel Poverty Action Lab, author of the book Poor Economics, author of a new book that's coming out next month called Good Economics Good Economics for Bad Times, coming out next month. And she's a great scientist at heart, I believe. In any case, the problem we started with is the one that I've already presented to you. Poor people in developing countries worldwide, including India, where all our work has been done, are at great risk of failing to learn up to their intrinsic potential in school, failing to learn reading, failing to learn mathematics. And the question was, what can we do to help them? And our hypothesis was that all children have the capacity to learn in school, and all children are now in school, but they're the first generation whom schooling is universal. And so most of them are living with parents and other adults and even older siblings who had no schooling whatsoever. So they don't have the support at home from literate, numerate adults and from the kinds of materials that encourage communication about number and geometry and learning of its symbols. So the hypothesis was that if we could create social games for these children to play and allow them to play them in preschool classrooms, maybe we could give them the kinds of experiences that make learning primary school mathematics achievable for more advantaged children. So our first experiment to test this was conducted on about 1,500 children in preschools in Delhi. And children were, at the level of the preschools were randomized for such that children within those preschools would either receive a set of math games, which consisted of 2 number games and 2 geometry games. They should all look familiar from my Math is Easy part of this talk. That was one group. A second group was given games that used the same kinds of materials and had the same kinds of rules and were, we hoped would be equally beneficial to kids, but they had nothing about number and geometry in them. We hoped they'd be beneficial for the development of basic social skills for learning from other people. And finally, we had a no treatment control. And children played the games for about 4 months. And both before they played and at 3 time points afterwards, we assessed their numerical skills, geometry skills, and a bunch of other things. Now, this study had many surprises in it for me. The first surprise was that although these kids had never played games before, they actually took to the games as readily and as effectively as the kids that we tested in Cambridge, Massachusetts, whose homes were probably replete with games of all sorts. There was very high similarity in the patterns of gameplay that we saw in these 2 otherwise very different populations. Now, consistent with that, when we look at how children did on our assessment measures, a couple of the assessment measures were assessing essentially the abilities that the games were exercising. Sensitivity to properties of geometric forms, sensitivity to relative numerosity of different sets of dots. So this is what you'd call near transfer, right? If the games were teaching anything, they should be teaching kids this. And in fact, what we see is that at the first end line, which was conducted within the first 3 months after the intervention ended, so 4-month intervention, and 0 to 3 months later, kids got this test, and we compared how they did at that first end line to how they had done at baseline against the performance in the no treatment control group. So basically, no treatment control changed from baseline to this first end line. That score is here, and anything above that is asking, above any natural improvement you'll see over the 4 months that have passed during this period, are we seeing above that any advantage from the intervention? And you see that for the kids who got the math games, there's a fairly substantial advantage, about 0.4 of a standard deviation better at the skills that the games were taught. Now, part of that seems to be a general effect of playing any sort of game, because these are the social games kids, and they're also showing an advantage there. But the difference between these 2 is real and reliable, and that's the effect of the mathematical content. Now, the second surprise was, at the end of this intervention, these games were taken away. Children never saw them again. But we tested them 6 months later, halfway through 1st grade and at the end of 1st grade. And the advantage was still there at each of those other time points. It didn't even seem to be really any smaller. So these kids, even though they hadn't gotten to play this stuff for a full year at this point, this was at the end of the 1st grade year, they're still showing higher sensitivity to number and geometry by about as big a margin as they did at the very beginning after the intervention ended. So I think this is saying that children are both deeply alike in the way they're able to take to activities that build on aspects of number and geometry that are intuitive to us. And when you give them that opportunity, it can have a lasting effect. So, but that's all not relevant to our primary question, which was, can we have an effect on how they do in school? And the answer to that was, well, if you look right after the games ended, the answer seems to be yes. However, right after the games ended, what you're testing are the aspects of number and geometry that they learned in preschool simultaneous with playing the games. And there you see an advantage. What we really want to know is, will that advantage carry over into a different context where now they're in primary school and they're actually learning primary school math? So the tests changed from the tests of preschool vocabulary and preschool reasoning tasks to primary school vocabulary and reasoning tasks. So in primary school, a circle is called a circle, it isn't called a ball anymore, and so forth. And the question was, will these kids be better at picking up on the primary school material for the experience that they had had in preschool? And the answer from this first study was a resounding no. The next time you hear an academic like me say, I did a study in the lab, and based on that study, here is how we should educate children, do not believe them, okay? You can't simply find things in the lab and generalize from them and expect them to work. You need to actually go into the field and see what works and what doesn't. And in this case, our first experiment, it did not work in fostering children's later mathematical development. So now we do what we always do in science. We get an unpredicted finding, and it leads us to rethink and ask, okay, why didn't it work, and what could we do differently? Well, one thing that was conspicuously absent from that first experiment was any exposure to the symbols of mathematics. We did have kids playing in groups, so they were getting exposed to mathematical language, but they weren't getting exposed to any other symbols. So we did a second experiment, basically the same method, except now we didn't have a social control. We only have math games, and we had two different kinds of math games. We had the intuitive math games that just use dots and forms. We had purely symbolic math games that never showed children dots, only showed them the symbols of, for numbers, and there was kind of a mixture of forms and symbols in the geometry versions of those games. And we had two other conditions. Mixed games, where kids alternated between playing with the intuitive and the symbolic materials, and a no-treatment control. And here, the findings looked quite different. So first of all, on the trained intuitive tasks, these measures, the findings looked pretty much the same as they did. They looked very good in the first study, and they looked very good in this study as well. So kids improved on the things that they were trained on, and a year later, that improvement was still there. So that was the same as the first study. But now on the school math skills, we find effects on the symbolic measures not only at the first end line, where they're just out of preschool, but also at the last end line, at the end of first grade. Now we're seeing an advantage, especially for the children who played the mixed games. They're doing as well on purely symbolic measures as the kids who played only the symbolic games, and much better than the kids who played this, with the symbolic games on the intuitive measures. So it looked like the mixed games were actually working. But now we had a further problem, and then this will be the last study I tell you about. We had a further problem that we had to solve. So the goal here is to educate the child population of India. I mean, eventually, when you work with an economist, that's the kind of ambitious goal that you have. And yet, we had games that could only be played by a single small group of children, maybe 6 children, with a single adult who we had brought into the classroom to be playing with the kids. If this is going to work across the board, then this has to be something that can be played by a whole classroom of children simultaneously without a special teacher coming in. It's got to be the regular teacher who's doing it. So we went back to the drawing board, and it took us like 2 years to get to the point where we were ready to tackle this sort of population of kids, right? Boisterous kids, 40 of them in a classroom, all playing at once, and a teacher who's busy with the regular curriculum and humoring us by taking some time away from the regular curriculum to play these games with the kids in his or her classroom. And we did this study at 2 grade levels. We did it with kindergarten kids and with first grade kids. These are children in Delhi government schools. The city of Delhi was an invaluable partner in this research. For the kindergarten, we developed different games for kindergarten versus first grade. In each case, the same sorts of games as had been used previously, but with material that was specifically coordinated with the school curriculum. So for example, in kindergarten, they only taught children numbers up to 20, so we tailored our games so that numbers only went up to 20. And in first grade, numbers went up to 50, and we tailored our games accordingly. Now the way that children played these games is we would take a full classroom, divide them into different groups of 4 to 6 kids, and have each group play cooperatively within the group, but in competition with the kids in the other groups. And teachers would keep track, and the kids would all keep track of which group got the best score on each given day, and they had like charts on the board where they could monitor against each other. But no individual child is ever put on the spot. Children are encouraged to work together as a group and to help each other get the answers, or even give them the answers for kids who are doing less well. And you see this kind of interaction going on throughout the gameplay. So the intervention itself had about 1,400 kids in each of the 2 grade levels, as I said, presented by regular teachers, and classes, and it was the simplest design because classes were simply randomized to either get the games or not. Now, the no treatment control is not a subtraction from the intervention, because the intervention was taking time away from the time that the teacher had to be teaching math. So the no treatment group had more math instruction than the treatment group did because of the time that the treatment group was playing the games. So the intervention went on for a full year, not 4 months. However, it was entirely at teachers' discretion how much or little they wanted to play, and the amount of the total amount of play was about comparable to what it had been in the earlier studies. And all we have at this point is 1 pre-test and 1 post-test of all of the kids at each of the 2 grade levels. So our questions are, this is what classrooms look like. Kindergarten classroom. Some of them didn't have desks, so kids are sitting on the floor in this classroom. Here's a first grade classroom, I believe, and you see all the different kids with their desks pulled together so that into tables so that they could play cooperatively. So the first question is, will these kinds of games work in a classroom? Will teachers accept them, or will they resent that we're taking time away from the curriculum? And will we see benefits in this higher stakes situation in which we are reducing the regular curriculum for them? Well, here's what we see for the kindergarten games, and I've graphed it differently. We've got all the math measures combined. The intuitive measures, these 2 are over here now, and here we have all of the symbolic measures. So this is the most important bar, and it's looking like both overall and on the symbolic measures, we're seeing positive effects for the kindergartners, so less of the regular curriculum, and having these games seems to be working. The effects are not reliable for the intuitive measures, though they're going in the right direction for the kindergartners. For the first graders, we're seeing pretty uniform effects across the board and all in the right direction, suggesting that these kinds of games actually can be useful in a pedagogical context for getting kids to treat math meaningfully, not as something where you put tally marks on a piece of paper so you come up with an answer that a teacher is happy with, but actually a meaningful activity that you can be using, that you then get empowered to use mathematics in creative and useful ways. So general lessons learned. I think I already gave you this one. Lab experiments in themselves do not provide recipes for school curricula. The best they can do is suggest hypotheses, and then we need research to test them. Now that research, field research, is likely going to show, I think, that your first guess about what to do will not be the optimal one. But like research in the lab, you're not limited to only taking one guess. You can do a succession of different field experiments and get closer and closer to something that could actually be useful to kids and enhance their learning. So back to my original question. I've taken this detour on educating the world, which is like, no small thing to be hoping to do. But behind this, there's another question, which is the basic question about the nature of human minds. What is it that enables us to embrace whole new systems of abstract knowledge in general, and in the case of mathematics in particular? Well, this is, of course, still a wide open question, but I do think that a combination of lab research in interdisciplinary cognitive science, as Molly was saying, and field research in classrooms can reveal universal properties of human minds. If you do field interventions that are based on things that are easy for infants, then there's a very good chance that if they work anywhere, they're going to work everywhere. Because an infant doesn't get to choose which environment they need to learn about. They come equipped with the capacities to learn about any environment you could put them in. So those capacities are going to be universal. And if they work anywhere, then we have a good chance, it seems to me there's a good chance they're going to be useful everywhere. What's more, these field experiments, I think, can actually shed light not only on the minds of children, but on our own minds. They not only tell us, I think, about how our minds developed, but about the very tools that we use now when we reason in abstract domains like the domain of mathematics. So if that's true, then we have something to thank the infants for shedding light on ourselves. So thank you.
Microphone's going to start soon. There we go. If anybody has any questions, you can raise your hand. I'll try to get the mic to you.
Thank you. It seems like infants have can easily distinguish small groups to big groups, and have a problem when the groups are too far apart.
Right.
I believe I read somewhere that the cutoff would be around 4. That animals or infants can count up to 4 or distinguish 4 objects, but cannot naturally go above that. After that,
right.
You have to compute and use math and abstract concept. So
right.
that would be, that goes along with your research. Like that's something that you observed as well.
Yes, I think that's right. But for adults as well, we can apprehend up to 4 objects in parallel. And if we have more, we need to be able to group them or organize them, compose them in some way. That's right. But that's not the only system that infants have. They have these other 3 systems. So if they're presented with a dense array of dots, then they can represent that there are approximately 16 dots in that array and distinguish it from an array of 8 dots or 32 dots. So that's also a numerical ability. Interestingly, Stan DeHaan and his collaborators recently showed that if you take adult professional mathematicians and give them hard verbal math problems to think about, and while they're thinking about them, you're imaging their brains, and you see this little region of the brain light up as they're thinking about those problems. When you give babies arrays of 16 dots, you see, and in a task where they have to distinguish them from 8 or 32, you see that same area light up. So there's continuity there, and that's a different system. It doesn't have a limit of 4. It has a different set of limits. I think in thinking about our minds, we need to be open to the possibility that there are multiple foundations for an abstract domain like mathematics. There isn't a single magic bullet that turns us in, that provides us with mathematical intuitions. We have intuitions about space for navigation. We have intuitions about visual forms. We have intuitions about these 2 different kinds of intuitions about number. And we have systems like language and pictorial symbols that we can use to bridge across these systems and move into new and more powerful territory. Yeah.
All right, any further questions? Yes.
Thank you. I was fascinated by when you explained that the games you gave the preschoolers didn't necessarily always translate long-term in primary school. Mm-hmm. I wondered if part of the difficulty is if what you're measuring in terms of learning mathematics in school is how to do school mathematics. And I'd be interested if what they learn in the preschool games translates to, say, mathematic tasks at home or outside the school environment.
Yeah.
And also how the social aspect of children teaching each other these games and the mathematics works, because I'm in sociology, mm-hmm. and I would like to explore the social aspect of
those questions
mathematics.
are spot on. Those are all the directions that I hope our work will go in as well. I mean, I think one possibility, it would be really interesting to see whether outside of school, these kids who were in that first study are showing any advantages in, say, shopping, doing calculations for purchasing things, or using math in other kinds of ways. That's very possible. We're going to be going back and studying them. They're in like 6th grade now. We're going to be going back and studying them, and that's one possibility. Here's another possibility. At the time that we conducted that study, the Delhi government may change their curricula. They're rethinking the curriculum. But at the time that we conducted that study, the first year of mathematics instruction was entirely focused on rote memorization. So it's possible that if your goal is just to pass some rote memory test, then the kind of intuitions that we were honing would not be that useful. But even under the traditional system, once the arithmetic facts were memorized, they were then, the subsequent years go on to cover much more meaningful material. So we're actually going back to test those kids again. And we want to see, it seems possible, for example, that once they get to the end of primary school, start getting into middle school, where geometry and number become much more intertwined and spatial symbols become really important for thinking about algebra and things like that, that maybe we'll see advantages at that point, a sleeper effect from our studies. I don't know if we will, but I love those ideas. But I also love the idea that the social context is really important. I think it's important in a number of different ways. One is that when you're interacting with other people, you need to be thinking about not only what's in your own mind, but what's in the other person's mind. Like, here you are, you're playing this cooperative game together. Did the other person, are they thinking about it in the right way or not? Are they paying attention to the right sets of actions they're supposed to be taking here or not? And thinking about that, I think, can also help you think about your own mind and think about, what do I understand here and what do I not understand? And that kind of social back and forth can be really important for a whole nother set of skills that are crucial for success in school, which is, it goes under the term learning to learn, right? Figuring out what you should be devoting your time to, what the gaps in your own knowledge are, how you should be studying, and what you should be taking from the instruction you're getting from other people. And yeah, I think this, the hope is that social games will give you that while also focusing on a particular domain. Yeah.
Hi. First of all, thank you. And I'm really excited by your findings. I'm also a student in cognitive development and preschool math. And I was just wondering, are your tasks, like scripts or videos, available anywhere?
Yes. So, Molly, where are our scripts and videos?
They can send me an email. And
all of our data are publicly available from the first experiment. The other 2 experiments aren't published yet, but the day they are, those data will be available also. But yeah, the material, right to Molly. Yeah, absolutely. It's all low-tech, concrete materials, all kind of based on card games and board games and things like that. Yeah.
All right, let's give our speaker another hand.